Okay, welcome everyone to my webinar on a free ultrasonic transducer simulation software, which you can use to do modal analysis on all. So my name is Hussein Shakani, and I am representing my company, Ultrasonic Advisors. And we're gonna, yeah, it's free. That's true. And I can explain some of the details about the mechanics behind it, but there's no cost to you to download this and use it. And I will pretty much just demonstrate and jump right in, pretty much, instead of saying something fancy, which I will at some point. So this webinar is sponsored by PI Technology, and I'll talk more about them later. They're not exactly sponsoring the product, but they are sponsoring this webinar. They're sponsoring the dissemination of this type of information to you all. So quickly, I just want to show you the program. All right, so you can go on my website, which is ultrasonicadvisors.com. If you signed up for the webinar, you're able to get there, and you go on this new tab I put here, simulation software, and you click here and you download the software from there, from this link here. And there's also a sample CAD file, so you don't have to create your own CAD just to start with. But it basically is pretty much everything you would expect to need and use with an ultrasonic transducer modal analysis. Define, import geometry. I'll increase this for the sake of it. So we're going to import geometry. You're going to define and assign materials. You're going to assign the piezo materials and the boundary conditions. You're going to generate the mesh. You're going to solve for the eigenfrequencies. You're going to find which one looks the best for your particular application, and you're going to plot the displacement, and you can iterate on this process in order to understand how to design your tools, or like change the horn, or what frequency you're driving at, or what's exactly happening at an unwanted frequency. And I'll explain a little more about how I made it and kind of how it's as accessible as it will be, as it is actually. But before we get into that and how to use the software, so the sponsor for this webinar is Piezo Technology, or PI Ceramic. They have a lot of experience in developing piezoelectric components, actuators, and transducers. They provide different formulations, very similar to many other ceramic suppliers. However, they do have a huge emphasis on quality and consistency, which is a real important point for devices, especially devices where the piezo crystals are just a small fraction of the entire cost of the product. It's worth spending extra time and resources and attention to who you choose as your ceramic supplier. You can afford to have better product. You should work with a company like PI Ceramic. And they make a bunch of other things. They're also pretty popular in the multi-layer ceramic area as well. So check out the link that I'll have in the sign up for this webinar. There's emails that I'll send out, and other marketing information always has links to them. But also importantly, my consulting company. So I consult with companies developing ultrasonic transducers of all different types for power ultrasonics, sensors. There are many types of transducers that I work with, both power delivery and in sensing. As I mentioned, I provide consulting calls, assembly, guidance, mechanical, simulations, as we're even going to talk about today, training and on-site consulting. So there's a whole bunch of areas I help companies in. So if you'd like to work with me, if you'd like to have kind of an expert-led analysis, because a lot of times I find teams are talented, but they're kind of scrambling to find their path, and they have to get stuck in every hole as they continue. Many teams continue on and persist, and they're able to get to a successful product, but it really doesn't have to be as hard as you're going to find it if you're going to be doing these type of projects without somebody experienced, without a ultrasonic, without ultrasonic advisors. So contact me through email, sign up for a intro call through my website. I'd be glad to talk to you about your application. So I guess without further ado, let's take a look at the program. And let me change the screen sharing here. New share here. And I pre-filled this out, but but I'll go through the steps for you as well. It works. I've tried it on a different computer, so this is not as clean as a beta launch as I would have normally would have liked. But we got to get things done and get things out there, and I need to hear some complaints on how it doesn't work or how it doesn't mesh, because I can solve some of those issues, but I really don't know what issues people will encounter until they use it. So the first step here is you need to import the geometry. And even before I get to that, I just want to point out, so this software, so I purchased the licensing or the sub-licensing capability from COMSOL. So this program runs off COMSOL in the background, but you as a user don't have to pay for it. You could say I already did pay for it. So therefore, it's legal for me to distribute paid or unpaid this software that I make on top of theirs. It's not as capable as their software, obviously, but but for specific applications, you can do everything you want, and you can probably even do it in a more streamlined fashion. So that's how that works. So you don't need COMSOL to run this. That's the nice thing. So I have a computer, doesn't have any COMSOL, doesn't have anything on it, no licenses for COMSOL, but I can install the I've already installed the software and used it on that other laptop. So you don't need, so you can have a new laptop, you have to connect to the internet, because that's how I have it downloaded, but I can also build a application where you don't even have to connect to the internet to be able to run it. But so the proprietary stuff is what I built on top of it. What is COMSOL's is the solution engine. This allows me to make a very competent product. Works very well, but it doesn't take my effort for the FEA solution piece and a lot of other pieces shown here. So that's very important to point out. And there are a couple other customers. I mean, sorry, customers. Oh, maybe it'll be my customers. Yeah, I'll get through some of the comments. So basically, you import a step file. Why not other types? I typically always use a step file myself, so I'm imposing that on you. And all software, usually all CAD programs, can export that. And this is 3D. This is not 2D software. This is not 2D. You need to export it in 3D. And there are like Fusion 360 is what I use. It's relatively inexpensive, and most people working in engineering companies have easy access to CAD programs, but don't have easy access to simulations, and especially that directed specifically toward ultrasonics. Although this simulation program can be used for any structure as long as you have enough RAM to run it, it won't complain. And I made some programming or developer choices when I decided to represent the rest of the program. So it is, in some cases, I feel like it's a little bit little bit cumbersome on the user, but at the same time, it provides all the functionality and even some interesting ways of interacting with the program itself. So when you open the program, you'll have these like materials already kind of populated. So I have copper, steel, titanium, aluminum. You notice that I can just write whatever I want in here. So these are actually just these are just placeholders. They're more like notes for you. What I really expect people to do at this point is to do print screen when you want to document your work. You print screen, so you have all your material properties, which we change all the time. Like, when I'm doing simulations for clients, I always notice myself changing these material properties and forgetting like what graph goes with what material property. I'm always forgetting that and having to export it, and it's so much easier just to like screenshot this, and so you know where you have what properties for copper and other things like that. So you can change these. So you can change the Poisson's ratio, like here. So what we basically do, so copper is already good. So what we're going to do is we're going to, so right now I've already selected this. Let's say I didn't select it already. So I import it. So you import, you import, and then you plot the geometry. And then you assign the materials. So that material goes there, and then you go material 2. So material 2 I chose for the bolt, so I would have to click this bolt in the back mass here. And material 3 is titanium, and this is aluminum. But you can change these properties. Before I actually had it as nylon, so I want to show you. Actually, go ahead and share screen. New share. This one. You know that one. This one. Okay. Share. So this is how it looks when you open the program without anything there. There's no aluminum. So what did I do? I just typed in the values for aluminum. You can't type in letters for material properties, but I just basically typed it in, and that's it. Then it's there. And there's only 4 materials that you can use at this point. That's just how I set it up. So it worked well. It worked well because I've already kind of piloted it with one of my clients, like this type of format. There's many improvements that can be done. I realize that, but it tends to have its benefits in the way that it's set up. So material 3 is not assigned anywhere. So there's no titanium in this ultrasonic cleaner. The front mass I have or the horn is aluminum. And I'll go through all the questions when I feel like it, I guess. But I will get through them. So this loss factor, this interesting here is maximum element size. So there's not as many knobs to turn for the element size for specifying the mesh, but this can help like right, and I'll show you about the elements in a second. So everyone can mute, I guess. Yeah, all right, we got muting. Actually, we're good. Anyways, okay. Yeah, so how am I assigning materials for the body? So you click this button, and let me actually do it this way. Let me start fresh. Share. Because I didn't want to run the program and have it not work. That's why I made sure to do it this way. So here I'm doing it. If you can see what am I sharing right now? Sharing. Oh yeah, I'm sharing this. So I just imported it, and then I press plot jump. I think somebody's mic is on here. Mute all. Okay. Mute all participants. Okay, good. There we go. Okay, so here we go. So we assign all the materials. So material 1 is and I click this button here. I click material 1. That's a button. So then I want that as the electrodes. Let's say copper electrodes, right? And then material 2 is steel. So that's the back mass and the bolt. And then material 3 is, I'll just leave titanium as is. So I'll just make this aluminum. And this is just for my own notes. Like me writing aluminum in there doesn't change anything. So the 0.33, the Young's modulus in pascals is 6.89 e to the 10. And then the density is 2700, and losses, this is a very ambiguous topic, but I just put something in there just cause. So material 2 is that. Material 4, which is aluminum, is the front. And then now we'll revisit this mesh in a second, but let's do the ceramic. So we're going to choose PCT4. And one thing I just want to mention, make sure you don't double assign materials. So the same geometry should not be selected twice anywhere. It's not that hard. There's not that many selections. You usually have to check your FEA. And there are no default geometries. You have to select them all. So the mesh will usually throw an error if you don't have if you don't select if you double select anyways, and it's very easy to kind of go through it. So PZT8 nothing, PZT5 nothing, PZT4 we're gonna assign it there. And click pull up. You have the polarizations in this program are either Z up or Z down, so you cannot have it X or Y or radial right now. So and then ground. So if you click this little wire box, I guess, and then you can zoom in there. So this is where one thing to note is where it's nice to have a mouse, but you can also do this using your mouse pad, is you have to do the middle scroll wheel, and then you can end up choosing different surfaces. So I click ground and then middle scroll wheel to select the surface in the back, and then I click there, and then I select that surface. Then for the voltage, where voltages would normally be applied, you have to select this voltage on the top and bottom part of the electrode. This is not like it's going to conduct through the electrode, so you only got to assign it on one side, which is what you would do in reality. This is simulation, so you have to assign if you have no electrode, let's say you're just making a very simple simulation, then you would just have to assign that one surface between the ceramics. But in this case, since there is an electrode of finite thickness, there's the top and bottom side of it, you have to assign the top and the bottom with voltage. And we'll undo this now. So that is there. The next thing I want to talk about is the roller boundary condition. So you can actually import three-dimensional, like fully revolved. I didn't do that because that's, say, if you do a quarter geometry or even more narrow, even more of a pizza slice, depending on how many slices you take at a time, you will actually use less and less mesh count. So if you want to have it more detailed, then you'd probably want to use more symmetry, use a smaller geometry via like symmetry and boundary conditions. So right now we have this as a sliced geometry, so we have to assign roller conditions. Right now, if I click it, nothing shows up. Well, why is that? Because I didn't assign anything. And I realize I talk really fast, so I apologize if what I'm saying is not always clear. I watch myself and I'm like, why am I talking so fast? It's because I have a lot to say. Okay, so I selected all of those boundaries, and if you don't select it, the nice thing is it doesn't take too long to solve. So you'll be able to see, like, if you forgot this boundary condition here, you're gonna get some mode where this is like resonating out of plane, and you're gonna correct it. You're just gonna run it again, you're gonna correct it. So let's mesh. So there's no preload. So, but that's a good question. So, a common thing, and I also see this with clients a lot, a common thing is that people want to put in preload because that's what happens in reality. The effect of preload in reality are a few. Preload changes face-to-face contact conditions between elements. It also ensures in reality, between the components, in reality, it also makes sure that everything stays together. And it also slightly deforms, preload also slightly deforms the whole structure. So addressing each of those one at a time, in reality, the amount that the geometry will change due to preload is very small. Like, so it's negligible. The next part is in reality we have changing of interface like acoustic properties of a wave traveling through an interface. When we preload it and the two components are more squished together, their faces become kind of more conforming to each other. That's not something that we represent in finite element analysis in almost all cases. It's too much of a detail. We're going to lump that in somewhere else. We're not going to look for that level of detail in our analyses. And the last one, that everything should stay together. That's why you need preload. Well, everything's already going to stay together in this. So we don't really need preload. You can actually introduce error by making your simulation more complicated in an effort to try to add insignificant or effects that you cannot model. So taking it too seriously. So the number of elements is 28,000 elements, and this takes about 20 seconds to solve when I'm not on Zoom, so I shouldn't take any more than that. So, and I set my search frequency, so it's going to search for 10 frequencies around this 40 kilohertz. So we can just click that button here, and maybe while it's solving, and nothing's freezing, I can so let me answer the questions from the most recent to the previous. Is this mesh all single body or is there contact? No, there's no, in this case I didn't put any contact. So they're all, it's conform, it's like you see here, they're all the points are kind of touching. This is problematic. Sometimes there's contact conditions defined, which makes the mesh less accurate, but it ensures that it will solve every time. And right now I do want to make a program that will work every time without too much fuss. So I may include that, and it's rather simple actually to change it if it ends up being a problem for users. The other questions. Okay, it finished. So there was this little bar that came up on the bottom, and it took about 20 seconds to 28 seconds. Okay, and loss factor. So yeah, so let's just take a look at the mesh real fast. So let's assume that we wanted to increase the mesh in the crystals or something like, or in the electrodes. So if you, and that's material 1. So if I make this 1 instead of 5 and solve the mesh again, it didn't do anything. So it did a little bit. So let's make it even smaller, 0.5. See, now we have 2 elements, and there's better ways to do this. I'm not saying this is the best way to do it, but if you really want more definition there, but typically we look at wavelength per, you know, like 10 elements per wavelength or something like that. But because of these, usually the way it looks is pretty well represented, and you can do a study where you convergence study basically, but we don't necessarily want this right now. We want this to be the 5 case, but I already solved it, so it's fine. So here we already solved that when I press solve resonance. So we're gonna go, this is the rigid kind of body mode. Oops, I pressed it again. So that's another little kink here. Don't press it again. I keep doing it. I need to disable it or put it somewhere far, like put the solution on a different, and this is the log, the console kind of, it does a log for you, so you can you will be able to, if you have issues or something, we can take a look at what that's saying. So there's a single mesh. I think it's called conformal, or it's called union in COMSOL, and it's called like something else in ANSYS. So here we plot displacement. This is the rigid body mode. If you had no roller boundaries, there would be 3 or more of them. So I think 6. But since we're roller constrained, that's not going to happen. I'm going to choose the first one, and this seems like the resonant mode of 37 kilohertz here. You're going to have to write this down, like 37.8, 37,846. You can't just copy it. Sorry. But we can, yeah, I can change things like that in the future. And anti-resonance. This is interesting. What I do in anti-resonance is all these that were assigned as voltage are now floating. So anti-resonance will be higher or lower. Who knows? Well, anti-resonance. So I click the button and the bar is loading here. And as you can see, there's probably going to be some action going on this side. And how many degrees of freedom does it say? It thinks I have 12 cores, but I don't. I think it's double counting. Yeah. So that's solving. So should the resonance be higher or lower? What do you guys think? Anti-resonance, lower, higher. And there's a, so it's higher, as you guys, actually this is not it. See, that's you got to choose the right mode here. Plot displacement. That's it. Although it's opposite. See, if you look at the resonance case, it's just a phase. I could probably have a negative kind of thing, like flip the sign of the displacement. So this is so it's 37.4 kilohertz, and the anti-resonance that shows up here is 42.791. And you know, as you know, the farther the distance between the resonance and anti-resonance, the more the crystals are at the node, so that's a good sign. So you'll be able to tell some of the characteristics of the impedance and in general. Also, obviously, if you're doing a anti-resonant device design, then you'd want to use the anti-resonant frequencies for that. So yes, so I have another thing here, which I did logarithmic, or actually we did, let's keep it linear, but we can do this. This helps you identify them, like you can use discrete instead of continuous, you can use discrete. Because let's say common thing that people do, like I purchased this ultrasonic device online and like I don't know where to hold it. I want to machine something in there and I don't know where to hold it. So what do we do here? So using this banded thing. So we see that there's zero displacement in the bolt. Well, that's not really a good place to hold it, but we do see, and if we can put the color bar up here, the lighter blue, it seems like there's the least displacement on this top face. So you don't want to, like, normal like logic would be, oh, grip it next to the horn because that's typically where we hold it. Well, in this transducer, it seems like it's better to grip it somewhere on this back side of the face. And if you are able to either elastically hold it in this case, that would be the best case scenario. And you can even see that there's a point which is similar to, which is a relatively low outward displacement. It's perhaps going up and down. But yeah, that would be maybe a good spot to hold it, even on this lighter blue color. So that could be, if you machine a groove there, you were able to hold it in that position. I think you could make it work. So yeah, this is the program, and you can save it. It's slightly awkward to save because it saves a new executable. So, but you can still open that executable again. So this is the program, and let me just now start to share the original screen again. New share. I mean the PowerPoint. Okay. So this is the transducer that we just modeled. I think I took the measurements from this, more or less. And here are some things to note, like you can go you go in your task manager. I'm not telling engineers something they don't know, but you can go in your task manager to see how much RAM they're taking. COMSOL itself also doesn't tell you how much RAM it's going to take before it goes ahead and does it. So you got to be RAM careful, RAM conscious. We're all encouraging all of our friends to be RAM conscious when doing simulations, or else they might take forever, right? So here's right now for changing material properties. Here's what I use. Basically you can just you can just type them in. Likely you're not going to be changing to 10 different material properties, or you're more interested in how density changes something. So these are the typical materials that we use, and I put speed of sound down here for reference. Bronze seems typically has a closer speed of sound to piezo materials. You can tell the other ones are higher, like how long to make a horn. To make a horn out of the same size titanium and steel, it seems like they're going to have a similar frequency, for example. So this is just honestly just typed in from Google, not Google, typed in on a spreadsheet from looking at material properties. I'll share this somewhere, but it's already in this slide, which is going to be given to you all. So installation. So you go to the website, which is here. You click this, download software, you try to open it, and then you're going to get a COMSOL runtime installation. And you just have to click through, and you have the license to use this software for free, because I pay for this. So I pay for the ability to create these kind of sub programs. So there's a question, how do you adjust PCT properties? You adjust PCT properties by paying me more money for it. No, right now I didn't have something to do that. It's usually not that important. But I guess there's some cases where you might want to get more into the analysis. So I don't have an option to do that at this point. But you can change between PCT 8, 4, and 5A, which should get you pretty good across the board in general. Right now I only have it for Windows, but it's not hard to do it for other computers. If you're extra nice, I might just do it for you. It's literally just like a checkbox, and it just exports all of them, like Apple Silicon, regular Apple, Linux ARM, Linux, and Windows. So it has all those kind of, and they all require different ways to interact with them in order for simulations to go faster. Actually, on my personal computer, for my this is a whole nother story, but my personal the computer that I use to do simulations on is a Mac, an Apple Silicon, and there's huge advantages to using it for simulations, and COMSOL takes advantage of what it has, but that's not something I'm getting into today. So eigenfrequency is very RAM heavy, so I would suggest using a laptop with 16 gigabytes or higher if possible, like 32 gigabytes, or yeah, I think, yeah, or 64. So this laptop here actually only has 32, but yeah, 8 gigabytes will be also okay. I tested this exact model on an 8 gigabyte one, and it worked fine. Obviously, take longer to run. So as like quick benchmark, like 30K elements, 6-core laptop, 4 gigabytes of RAM. This solution takes this solution goes in yeah, 26 seconds. If you have 90K elements, it'll take 2 minutes, which is not a lot of money if you work, you work by the hour. But it's, yeah, this is how long it takes. So it's relatively quick, and that's usually how eigenfrequency analysis goes. You do need the RAM to support it, though. That's what I can say. And I might do, I'm hoping probably as I continue to develop it, I can maybe do some more frequent webinars, which would just go over some basic cases, or just honestly, even how do you make a structure. I don't have a geometry creation built in here. It's a little bit cumbersome to do in COMSOL unless you're doing parameter analysis. But yeah, like, look, well, some things that I'm thinking about are just, general, general usability and, improvement, like material properties, like making that easier. One thing I forgot to mention, and if I'm sure you guys are still at the edge of your seats, I caught all 14 of you. So one clever thing that I put in here is that these materials are meshed in order. So what happens is that material 1 is meshed first, then the piezo, then 2, then 3, then 4. What this means is that you can because you want to mesh the material that's the most dense in mesh first. That's why there's like an inherent selection in order. So there is a difference between you using material 2 as copper and material and the electrode versus material 1, because depending on what's going to be meshed first or second. You can actually assign multiple mesh for multiple materials. So you can have material 2 and 3 be steel, but have them be different element sizes. If you want to increase your elements in other ways, like let's say you want 2 elements in the electrodes, you can just split the electrodes in 2 in your CAD program. You split the electrodes in half so that you have two like thin electrodes instead of one big one. And that way you'll just inherently have two elements in the thickness, for example. And COMSOL by default here, it uses quadratic mesh. There is like a midpoint, and you don't need as many elements as you might believe, just from looking at the mesh there. And I also wanted to mention the other nice thing about doing a segmented, or like a quarter model, like you cut the models that you can see the mesh on the inside. I don't have different mesh analysis methods. It's more, you're more going to need to take a look at the model to see if it has the elements in the right places at this point. But usually for modal analysis, we're not as concerned. Typically convergence, like I did some convergence, like these two simulations had pretty much the same same frequency, and we also don't want to take finite element analysis too seriously. You want to get to prototyping. You want a finite element not to be like a place you get stuck. You want it to be a place that allows you to build something meaningful, after which you will come back. So with that, I'll take questions. So right now we'll do questions in the chat so then I can still have everything recorded. And then after that I can have a minute or two or 5 minutes or 10 minutes maybe regarding questions that you don't want recorded. And I'll just do this here. So we have questions. So can you talk about the differences we might see using this COMSOL method versus modal analysis in Fusion 360? So Fusion 360, you have to pay every time you use it. I don't know if you use more. So we're talking about Fusion 360 modal. What really pushed me to make this and got me very upset is that Fusion 360, they changed their simulation thing from like you can do unlimited modal analysis to you have to do it there. You have to pay every time you buy these tokens, and it's just like, I don't like that. Um, so that's one big difference. The other one's like modeling a piezo. They have roller boundary conditions in Fusion too. There's the kind of mesh, the loss factor. I didn't get into the loss factor. I forgot about that. So if you see here, let me just do a print screen and bring this up a little bit better. Okay. I'll just make a new slide here. If you see this, this value here, it has an imaginary and a real part. So if you divide both of those like 95, or you do 37841, which is the frequency, the real part divided by 95.9, that equals the Q factor of that specific mode. So that's that's one thing I forgot to mention, but yeah, Fusion 360 works, and I've recommended clients to use it. I've even used it for paid projects, but when they change their system to do like pay buy tokens and stuff, that yeah, then I can't advocate. I don't advocate it anymore. It's not like cost effective. So will I be adding stress loading conditions like pre-stress? I think you're talking like pre-stress. Right now, I don't have the traditional COMSOL license to do pre-stress analysis, like both pre-stress, which takes a specific. But yes, there's a way to do pre-stress, and I talked about it before by slicing the center. So you can having the ability to compare static and dynamic loads are important, or at least how effective your preload is being distributed. That's very important. So so basically, yes to static analysis, probably no to pre-stressed frequency response. Yeah, and I will, yeah. So let me conclude the recording, and then maybe I can get, if some people want to, they can share some suggestions, or I even have some questions too. So thank you for joining this webinar, and I will see you in the next one. And you'll be on if you're on my email list, you'll get that. If you sign up for the webinar, I put you on the list, so you'll get the links and whatnot, but they're already on my website because I decided not to put them behind a email campaign, I guess. Yeah. All right. Thank you all.